Shocking discovery: Earth bacteria found in Ryugu asteroid samples. Back in 2020, a Japanese mission successfully returned samples from a massive near-Earth asteroid called Ryugu. But surprisingly, while analyzing these samples, scientists found living bacteria, making one of the most unexpected twists in the search for alien life. Now some researchers are speculating that this could actually be life from Earth, as similar contamination was seen in the Apollo moon rocks and Martian meteorites. But with NASA's strict procedures in place, is contamination even possible? Or could this be evidence of life beyond our planet? Join us as we explore the science behind the life found in these asteroid samples, discover how even the strictest precautions could fall short, and see what it means for future missions. For centuries, scientists have been obsessed with asteroids, massive space rocks hurtling wildly through space. And honestly, it makes sense, as these celestial objects are ancient time capsules holding secrets about how our solar system came to be. Think about it. At the very beginning of the solar system, a massive disk of gas and dust began to form. Tiny particles collided, stuck together, and grew into larger fragments. Eventually, the largest of these became the planets we know today. But some of the leftover pieces never coalesced into planets. These are the asteroids. So our fascination with these massive rocks orbiting the Sun for the past 4.5 billion years stems from our desire to understand what planets are made of, how they form, and how they have evolved. But the discovery of some asteroids has done much more than that. Retrieved samples from the asteroids have unraveled far more intriguing and unexpected discoveries than we ever anticipated. And that was the case with 162173 Ryugu. On December 3, 2014, the Japanese spacecraft Hayabusa 2 was launched with a singular goal: to retrieve samples from the 900-meter or 3,000-foot asteroid called Ryugu. This fascinating asteroid was chosen because it is believed to be a treasure trove of primordial material, untouched since the birth of the solar system. For nearly 4 years, Hayabusa 2 traveled across millions of miles, its instruments calibrated to perfection. Finally, it arrived in June of 2018, and in 2020 it was back on Earth. This marked a groundbreaking moment in space exploration, as it was the first mission designed to return pristine samples directly from an asteroid surface. While scientists have studied meteorites, fragments of asteroids that fall to Earth, for centuries, they're rarely pristine. Even brief exposure to Earth's atmosphere alters their composition. Rain, oxygen, and microbial contamination immediately begin to change the material, making it impossible to study these rocks in their original state. By collecting samples directly from Ryugu and transporting them in sealed containers, Hayabusa 2 ensured a level of purity that meteorites simply could not offer. So what's the interesting finding we made from the Ryugu samples? Now, with the success of the mission, Hayabusa 2 returned its precious cargo to Earth in December of 2020, and scientists began analyzing the samples in clean rooms, free from contamination. More than just physical samples, the mission also provided an extraordinary visual record of Ryugu's surface. For many scientists, these images are as fascinating as photographs of the Moon, Venus, or Mars. Asteroids, with their low-gravity environments and alien landscapes, offer a unique window into the mysteries of our solar system. Ryugu, however, turned out to be far stranger than anyone expected. Discovered in 1999, this asteroid is a member of the Apollo group of near-Earth asteroids. These objects cross Earth's orbit, and while Ryugu is not an immediate threat, it is classified as potentially hazardous. If it ever struck Earth, it wouldn't be on the scale of the dinosaur-killing asteroid. Ryugu is only about 900 meters wide compared to the 10 to 15 kilometer behemoth that entered the Cretaceous period. Still, its impact would create a massive crater and cause significant damage. The samples returned from Ryugu have already revealed an unusual and complex history. Isotope analysis suggests that Ryugu originated in the outer solar system, forming around 2 million years after the solar system itself began to take shape. The samples are rich in deuterium, nitrogen-15, and other isotopes like titanium, chromium, and molybdenum, clear signatures of an origin in the icy debris field regions beyond Jupiter. But here's where it gets even stranger. Ryugu samples contain grains that could only have formed at extremely high temperatures, around 1000 degrees Celsius, for a sustained period. This suggests that the asteroid didn't stay in the cold outer solar system, but migrated inward, spending time much closer to the Sun before eventually moving back to its current orbit. One intriguing hypothesis is that Ryugu may be an extinct comet rather than a typical asteroid. The line between comets and asteroids is blurry. Comets, with their icy cores, often lose their volatile materials over time and begin to resemble rocky asteroids. Similarly, certain asteroids can develop a coma and tail if they outgas volatile compounds. Adding to the mystery, Ryugu samples show evidence of liquid water activity in its past. Shortly after leaving the outer solar system, Ryugu experienced temperatures of about 50 degrees Celsius, enough to cause water to alter its rocky structure. Silicates became hydrated and iron transformed into magnetite. This suggests a brief period of heating, likely caused by radioactive decay or collisions that changed its composition. There's also evidence that Ryugu was once part of a much larger body, possibly 100 kilometers across. A catastrophic collision with an object roughly 10 kilometers wide shattered this parent body, leaving Ryugu as one of the fragments. This violent history, combined with its unusual migration path and possible cometary origins, make Ryugu a unique object of study. These fragments of the asteroid also have proven to be exceptionally well preserved, particularly in their ability to retain magnetic field data. What's more, the material is surprisingly soft, a feature that hints at a potentially comet-like origin, although softness isn't exclusive to comets. Some stony meteorites, for instance, can crumble at the slightest touch, while others are as durable as marble. A catastrophic impact with an object roughly 10 kilometers wide shattered this parent body, leaving Ryugu as one of its fragments. But the real revelations came from detailed chemical analysis of the returned samples. Among the most exciting discoveries was uracil, one of the 4 key components of RNA. While uracil itself doesn't require life to form, it is essential for the creation of RNA, a molecule central to the biology of life. Alongside uracil, researchers identified 20 amino acids and even vitamin B3 compounds that are not products of life, but are heavily utilized by living organisms. This raises the possibility that asteroids like Ryugu may have delivered these building blocks to Earth during its early history, potentially contributing to the origins of life. These findings bring Ryugu into the broader context of carbonaceous chondrites, a rare type of meteorite rich in carbon. 2 notable examples, the Allende and Murchison meteorites, offer critical comparisons to Ryugu's material. The Allende meteorite, observed to fall over Chihuahua, Mexico in 1969, is one of the most studied meteorites of all time. When it broke apart in the atmosphere, it scattered nearly 2 tons of material. Allende is famous for its chondrules, tiny pebbles that formed in the early solar system. These chondrules bear tiny black marks, trillions of them per centimeter, caused by radiation damage. This phenomenon, also seen in lunar rocks, points to exposure to cosmic radiation at a time when Earth's atmosphere and magnetic field shielded its surface. What's particularly striking about Allende is its isotopic composition. It contains elements like calcium, barium, and neodymium in unusual ratios, suggesting they originated from outside the solar system. These findings support the theory that our solar system formed near a supernova, and the shock waves from that massive explosion may have triggered the collapse of the molecular cloud that eventually became the Sun and its planets. The meteorite also contains aluminum-26, a rare isotope with a short half-life, which helped researchers date the supernova to less than 2 million years before the solar system's formation. The Murchison meteorite, which fell in Australia just months after Allende, further complements this narrative. Like Allende, Murchison is a carbonaceous chondrite and is packed with organic compounds, including amino acids. Its fragments also contained pre-solar grains, particles older than the Sun itself, dating back 5.5 billion years. However, both Allende and Murchison were exposed to Earth's environment, introducing an unavoidable element of contamination. This is where Ryugu samples shine. Unlike meteorites that have fallen to Earth, Ryugu's material was carefully collected and preserved in space, ensuring it remained pristine. The ability to study these uncontaminated samples allows scientists to confirm findings from meteorites like Allende and Murchison without the lingering question of terrestrial contamination. Hey everyone, just a quick pause. If you're enjoying this video, please like it, subscribe, and tap that bell for instant updates. Now, let's talk about the contamination. How was the contamination of Ryugu even possible? For context, Ryugu is about 95,757,205 kilometers from Earth. That really puts into perspective how wild it is to think about living bacteria from our planet making the trip. So how did these samples end up getting contaminated? To understand the possible contamination story of Ryugu samples, let's go back to when they were retrieved. These samples from the Hayabusa 2 mission were stored under very, very strict conditions. Upon their return to Earth, they were stored in a hermetically sealed chamber inside the re-entry vehicle and were only opened in a nitrogen-purged clean room to prevent contamination. Tools were sterilized and the nitrogen environment was meticulously maintained. Yet despite these precautions, contamination occurred. The problem began when one of the samples was embedded in an epoxy resin block to prepare it for analysis under a scanning electron microscope. During the study, researchers noticed something unusual. Filament-like structures and rod-shaped organic forms began to appear. These resembled filament-producing microorganisms commonly found on Earth. Even more puzzling, the abundance of these filaments changed over time, suggesting the microorganisms were growing and then declining, a sign of a living prokaryotic colony. At first glance, this seemed like clear evidence of earthly contamination. Population statistics supported this, pointing to an origin linked to terrestrial microbes. However, the possibility that these microorganisms were indigenous to Ryugu couldn't be entirely dismissed. After all, Ryugu's environment, shaped by ancient water activity and organic chemistry, isn't entirely alien to the concept of microbial life. This conundrum highlights the persistent challenge of space exploration: contamination. NASA and other space agencies take extraordinary measures to sterilize spacecraft, particularly for missions to Mars and other potentially habitable environments. Yet, even with these safeguards, microorganisms have proven remarkably resilient. There are some fascinating situations of microbes thriving in NASA's clean rooms, arguably the most contamination-free environments on Earth. These microbes don't just survive despite rigorous sterilization efforts. They adapt and even thrive on the very cleaning agents meant to destroy them. One officially confirmed example is a bacterium called Acinetobacter baumannii. This resilient microbe can consume cleaning products as a food source, grow on ethanol and isopropyl alcohol, and even withstand hydrogen peroxide, outcompeting other organisms in certain niches. It's entirely possible that something similar occurred in this case. The rapid colonization of Ryugu's material by microorganisms raises deeper questions about life's resilience and adaptability. How did contamination occur so quickly, even under stringent controls? And what does this tell us about life's ability to survive in extreme or alien environments? One possible implication is for the theory of lithopanspermia, the idea that life can hitch a ride on rocks traveling between planets. If microorganisms can so readily colonize extraterrestrial material under Earth's conditions, it's not hard to imagine life doing the same across planetary systems. This also ties into broader questions about abiogenesis, the origin of life itself. All life on Earth shares a common genetic ancestor. But why didn't abiogenesis occur multiple times, leading to entirely separate branches of life? One possibility is that abiogenesis is so rare that it only happens once. Yet this seems unlikely given that life arose on Earth as soon as conditions allowed, suggesting either panspermia or abiogenesis isn't as improbable as it seems. Another hypothesis is that Earth's early life monopolized every habitable niche so rapidly that any new emergent life forms were outcompeted into extinction. This idea, supported by the Ryugu contamination, suggests that pre-existing life is so dominant that it can quickly colonize and overtake new environments, even those of extraterrestrial origin. Interestingly, this contamination event has also yielded valuable insights. It demonstrated that Earth's microorganisms can metabolize and grow using extraterrestrial organic materials, indicating that microbes might not require planetary environments to survive. Warm asteroids like Ryugu, which once hosted liquid water chemistry, could potentially have been hospitable for microbial life, whether arising there through abiogenesis or introduced through impact-driven lithopanspermia. While the contamination of Ryugu samples was a setback in some respects, it underscores the complexity of studying extraterrestrial materials and the resilience of life itself. And that's a wrap for today's video. Do you think there is still a possibility that we will find life outside Earth? And is it even worth the search? Feel free to leave your answers in the comments below. If you liked the video, then you should check out the one on your screen. This video on the 9 most convincing answers to the Fermi paradox will blow your mind. Don't miss this if you are interested in the search for life outside our planet. Thanks for watching.